First of all, I'd like to thank all of you for attending this session today. And I would also like to thank the organizers of the meeting for inviting me to be with you. Another title that is fairly relevant to the situation we find ourselves in as grain crop producers and people who do research is how we're going to use precision technologies when we're faced with high costs and low returns in our grain crop production systems. The outline that I intend to follow is first to give you some feeling for my appreciation of our current economic and social context, talk about how precision technologies were adopted in Kentucky, the state where I work, a little bit about where we are in Kentucky, where we think we might be going, and I'm going to use 3 examples as part of that presentation. And then from there, I'll move to a conclusion. In the United States, farm-level prices certainly have changed over this last couple decades, but for the most part, we're starting to see a major decline, which we're all facing. The previous slide, in my opinion, was fairly optimistic because it showed an increase, as you see over here. A number of economists have predicted flat prices for the next several years, and a few have decided that prices may go even lower if indeed the amount of grain in the world continues to rise. The social context for information has been changing in my country and in yours. We're in the middle of a certain kind of revolution. I call it a digital revolution. And we're replacing my favorite field, as a number of my students in the audience will tell you. We're replacing the field of chemistry, the field of the atoms, with bits. We're replacing use of inputs with information to help guide us to better use of that information, of that chemistry. But one of the challenges we face, particularly with the millennial generation that I have as students in my classroom, is they want information to be free. My colleagues who are journalists, I just spent several hours with one on a plane, complain about the fact that information, the desire for that information to be free, has caused these newspapers, news magazines, to become less prosperous. In fact, several have gone out of business. But in agriculture, we're faced with an opposite problem. Information takes time and capital, sometimes in the form of sensors or machines, to acquire, and all of that equals money. So we're faced with an opposite problem. There's a number of models for the adoption of technology, and 2 of them are shown here. This is the classical model where we look at the population of growers, let's say. We have some early adapters, then we have the early majority, the late group, and the people that lag behind. And we have a chasm here that reflects the fact that if we have this other model called the hype cycle, for hyperbolic presentation, I might add, where we have the triggers, we have this inflated expectation of what the technology is going to do for us. We have a crash here because of disillusionment. And then, as we learn better where and where not to apply technology, we arrive at other points. In my country, I'm going to use the social media as my prime example, where we can see that a number of different entities, Google+, this is Facebook, have done pretty well, but some have crashed. They never got out of the trough, but now we're seeing some new emerging things like Twitter and LinkedIn, which look to be reasonably successful. So some will succeed and some will not. There are some unforeseen consequences. This is the progression of students coming into my classroom usually. If you follow any of these zombie shows on television, you'll know exactly what these people look like. Moving forward to our examples, the first one I'm going to talk about, this line is supposed to go over here towards this one. The three examples I'm going to talk about in terms of this hyperbolic cycle here are auto steering and guidance systems for machines, then the grid soil sampling or grid soil mapping, and then yield mapping. That's going to be my third example. Auto steering and guidance are doing very well in Kentucky and in much of the United States. A lot of our growers are older. The average age is probably close to 58. Many of our farm sizes are right at 1,000 hectares. Therefore, the number of personnel, the number of people that are working in those farms is primarily family with one or two hired employees. So the owner-operator is looking for something to reduce fatigue and to improve machinery efficiency. They can get 1 to 4 more hours per day from the same machine. That was a substantial improvement in efficiency. So this technology has been widely adopted, particularly with tillage, planting, fertilization, spraying, and harvest. This is an example of an auto steering system on a tractor that is applying nitrogen fertilizer in the spring of the year. The passes are alternating passes so that the implement does not have to make a sharp turn at the end, but yet very precisely match the gap that's created when it makes an alternate pass. This is another example where, to avoid the damage to the planter that occurs in no-till systems with these heavy stalks, the rotated crop of soybean is planted directly between the rows where the contact with the old corn stalks will be minimal. On the other hand, if you're auto steering, you need to pay attention for obstacles in the field, or better yet, you need to have them programmed and mapped out before you begin. This is a true example, by the way, where they thought they could run the machine without an operator. Another application of this has been to interplant. Growers have been experimenting with this technology because in the United States, auto steering is something the grower completely owns. Once the engineer or the dealership helps set this up, the grower owns all of it, and the grower then feels much more free to experiment, to look for new applications, and to be able to find other ways to make this technology pay. Interplanting into existing wheat was probably one of the first applications, but there have been other applications looking at different placements of seed and fertilizer, using auto steer and guidance to bring those to the right distance under different conditions. Another major application has been with guidance to put section control on these long booms that go over the crop, either with sprayers or the long wings that are on planters. The major benefit of this has been to avoid overlap applications of seed, or pesticides. In Kentucky, many fields are not very regular in shape. They are not square, and they are not rectangular. So you have a lot of potential for overlap. In our fields, we actually save closer to 10 to 15% of input cost once this technology became widely utilized. But in the Midwest, where they have more of the square rectangular areas, they've been able to save 5 to 10% of input cost. But another major benefit that's not well documented is they avoid crop damage with overlapping application, particularly of herbicide. You can have some pretty spectacular achievements. This is done with section control and guidance to tell them exactly when to cut off the planter. This is done with boom section control. And this is actually an application in turf grass at a golf course. But engineers are continually looking for new opportunities in agricultural materials, and they've decided they want to look at GPS-guided implements, particularly when you're trying to plant on slopes or on the contour. Whether or not these give us increased yield or value is still a question. In this application, the planter knows it needs to stay over here. The tractor has drifted, but the GPS unit causes this hitch to shift over so that the planter line follows this, even though the tractor is offset slightly. So you have separate implement control here. Obviously, this is what they would like to achieve, and this is what they would like to avoid. Grid soil sampling has been a challenge in Kentucky and in much of the United States because of the cost. It's a good technology. It supports the variable rate application of nutrients and lime. And it has the ability to redistribute inputs from where they are not needed to where they are needed. It was very popular at the beginning. But the problems developed because there were greater sampling and sample analysis costs. And even though growers expected significant input savings, these did not occur. And the question was, why? What happened? This is an example of a field that has been grid sampled without any consideration except to put a grid over the top of the field. There were some reasons why these savings were not found when that procedure was followed. In the United States, most of the grid sampling and most of the other soil sampling is actually done by the fertilizer dealers. They do the analysis in a laboratory or contract it, and the recommendations are provided to the growers from them. The higher sampling cost was added to the fertilizer and lime prices for all growers. And the sellers generally follow a maintenance philosophy, which in my personal opinion, really results in the maintenance of the sales of fertilizer. Now, this is a reflection of a long-standing seller, fertilizer dealer, seller, grower relationship that exists in the United States. It has been efficient, but on the other hand, it is also probably the root of a number of challenges. So going back to what's happening, there's been a major attempt to then try to reduce costs. And the first thing that was done was to reduce the number of samples taken per field. Another thing was that the original specification, one sample for every 1 hectare, lacked in many areas scientific support. Also, there was a question, how much spatial variation can the applicator really manage? And what is the cost of that management relative to the value of the redistributed nutrients? In this example, we have a field that was sampled in 70 different places on a grid, and this is the soil test phosphorus map that resulted. This particular map shows the recommendations in fertilizer rates, and now they're in steps. The steps over here range in 0, 30, up to 120 kilograms of P2O5 per hectare. But the map is very detailed and is very difficult for a fertilizer applicator to deal with. If we reduce the number of samples in a logical way, increasing the area per sample, we get a different kind of a map that is more friendly to the applicator. More of the spatial variation is still captured by the map, but we also have the ability, in this case, to better deal with the situation. I'm not advancing slides. Go to the next one. There we go. If you reduce sample numbers too much, you end up with a map that is really a pretty picture, but is not a reflection of the variation that really exists in the field. So you can go too low in terms of the number of samples. But certainly going from 70 to 20 was a real cost reduction. Some other questions came up. Do I really need to use this procedure on every field? Can you, in your research, help me understand when or when not to grid sample a field? We studied 46 fields in one region of the state. These fields were in a corn and soybean rotation, and they averaged somewhere between 14 and 56 hectares in size. For those of you who may not know where we are, Kentucky is located just west of the Mississippi River, which kind of runs right up through here. So, sorry, just east of it. So we're in the heart of the eastern part of the United States. And in the state, these fields were located in this region here. I'm only going to pick potash. Potassium is a problem in Kentucky. To get top yields of both corn and soybean, you really need to maintain a reasonable level of soil test potassium. Our soils are older than many of the soils in Argentina, and this is why potassium fertilization is required here. This graph illustrates the amount of potassium redistributed within the 46 fields, ranging here from 0 to 45 kilograms of K2O per hectare. This is the average for any one field versus the variability within that field that we measured. And yes, there's a positive relationship. So the more variability you have within a given field, the more fertilizer you will redistribute. But we also decided that was pretty obvious. So we went looking for some other information. This is the average potash redistributed again, so it's the same numbers on the y-axis, but this is what is the proportion of the area of the field that even receives potassium fertilizer versus the whole field. There were fields in here where only 20% of the field was going to get any potassium at all, and that had a very low amount of redistribution and therefore less ability to pay for the redistribution of that material. Yes, there were some fields, particularly these few in here, where when the distribution got, say, above 50%, we were able to see some greater benefits. This is my same 45 fields again. Okay. This is the average soil test potassium for all the grids within a field. You might say, why does this have this interesting peak in the data? Well, it turns out the university recommendation becomes 0 at 150 ppm. So as the field average starts to move ahead of that cutoff value, then the proportion of the field that's going to receive any fertilizer at all starts to fall. Some fields actually had an average of 0, and therefore we don't need to be as worried in these fields about grid sampling. We also had a few at this end where the field was so low that we needed potassium on all the field at a fairly high rate. So again, there wasn't much benefit to grid sampling. The real benefit to grid sampling is in this middle area just before you reach an average value that's close to where our recommendations cut off. But the red line is got the price information. If I spend $5 per acre or $12 per hectare on grid sampling, if my potash price is $300 US per English ton, which works out to be 55 cents US per kilogram of K2O, I need to redistribute 22.4 kilograms of potassium per hectare, and that's the red line. And above that, I only have 8 fields out of 46 that qualify on the basis of potash alone. Some of these fields did need phosphate to be redistributed, and some fields needed lime to be redistributed. So it could be that the grid sampling would pay if these other nutrients got involved, and that worked out to be, it did move it up to about 18. Still not a good situation. So from our data, we concluded that very few of our fields qualified in a scientific manner for grid soil sampling. The average soil test was too low or too high, and there simply was not enough variability. We came up with an algorithm based on statistics to help the dealers and the growers understand, by taking a few preliminary samples, whether a field was a candidate for grid sampling or not. So when not to grid sample depends a little bit on your cost to nutrient value ratio. Since this data were generated, grid sampling costs have gotten closer to $8 per acre, but the value of potash, for example, has gone up from $300 US per English ton to over $500 US per English ton. And you do need to consider all soil test nutrients. But in Argentina, what's going to be the big one? It's going to be phosphorus. And are you going to earn enough from phosphorus to do this? If we're going to have fewer grids, the industry answer has been to make zones. Zone samples, if you have fewer zones than grids, they tend to lower the cost. But it also assumes that the soil test variability between the zones is greater than the variability within the zones, and there is not as much scientific rationale for that in my country as might be desired. The basis for the zones can be the old grid map. It could be a soil survey or electrical conductance map, or they can be and have been yield maps. This is an example where on this side we have a map where they used the old grid and a soil survey map, but they ended up, they moved the point around, but they ended up taking almost as many samples as they had originally. The other side, we have an electrical conductance map done with a Veris machine. But again, they take a lot of samples here and don't achieve much cost reduction. This example is a little different. A yield map was used, and there was a lot of reduction in the amount and number of samples. They moved them, but there's many fewer being taken. These are actually about 5-hectare sections, so there's much fewer samples being taken. Well, that's what we're facing in that area. So grid sampling is not quite as much favored, and we will see significantly less of that in the 2016 production season. We saw less of it this year. Let's move to my third part, which is yield mapping. Biggest problem we have with yield mapping is how do we keep finding value as we keep making more maps? When have you mapped yield enough on a field? Initially, yield monitors were very popular, but the data loggers for making the maps came later. We had many of the first machines had a yield monitor, but they didn't really have a logger to log the data so that you could create a map. Initially, we used our yield maps to find real problems in these. In Kentucky, the biggest single problem were wet, poorly drained portions of a field. We also had some areas with erosion and some areas with low pH. Salinity was used as a driver in the western states, and I mention it here, but it is not a factor in Kentucky. What they did was they would use the yield map and calculate the yield difference between the good area and the poorly drained area, calculate a cost-benefit ratio, and then decide whether or not they could afford the drainage to remove the excess water from that part of the field. It was done very successfully. Yield maps contain a great deal of data, but the data also means you have to have greater computing cost, you have to invest time, you have to understand software and hardware, and a large number of our older producers did not want to make that intellectual and emotional investment. Frankly, there is only so much you can ask your wife or your son or your daughter to do. So instead, the yield data was sent out to consultants, to a fertilizer dealer, or to a machinery dealer like John Deere, or to the input manufacturers. The latest thing has been to send it to big operations like Monsanto and Climate Corporation. I call that sending it to the cloud. But the whole idea is once you send your information to them, if you get anything back, you have to pay for it. And you may not own that data either. This is an example of a soybean yield map from Kentucky where these red areas are a true reflection of a drainage problem. And in this particular field, they probably could install some tiles or other means of removing that water and improving yield. And you can see here, these yields, which are probably close to this end, are about only 60% of the good areas. So it's a real value. Another problem, in my opinion, is that yield maps tend to find the obvious. We've seen yield versus soil map units. We've seen yield versus topography or elevation changes in Kentucky. And we've seen yields versus weeds, poor stands, and other things. A number of these, like drainage, are readily correctable. We can change the pH, we can kill the weeds, we can change the plant population to try to improve yield performance. But a number of them are not correctable. So the yield map finds the obvious, and the obvious is not terribly correctable. By example, I'm going to use this field from central Kentucky. This is a yield map for maize of a field. You can see we have some good areas here, and then we have some pretty poor areas around these edges. This is a digital elevation map that was developed for this field, and now you see pretty quickly this is a pretty steep area here, and some steepness over here. And when you figure out with your engineer how to put one over the top of the other one, The digital lines, this is the digital elevation map lines, show that this flat area in the middle is where the best yields are. And all these lines here mean that this is dropping off rapidly in elevation, meaning it's probably eroded, and that accounts for all these lower yields down in here. Pretty obvious. And not much you can do with it, and not much value you get from it. This is another example for a field nearby. Again, the digital map clearly shows in areas of rapid elevation change, we've had losses of topsoil, presumably. But in areas without that, we have the highest yield potential in the field. The other problem is we have some maps that resist analysis. We don't have an easy explanation or even a hard explanation for why they give the pattern they give. Was it the climate? Was it a nitrogen loss? Or was it a poor stand? This particular field, which is a field a few miles away, we have some really good maize in this area, 10 to 12 metric tons. And then we got some really poor areas that tend to ring around it. And we could never figure out what was going on. So what are we doing now? Well, after the obvious got over with, we struggled to give more value to yield maps. Some people are getting multiple years and doing yield stability analysis. Some are using them as input maps, changing the seeding rates, which has been worked for us. We particularly have recommendations for changing corn seed rates. And we also are now finishing research looking at increasing soybean seeding rates on poor soils. Some people used them to make profit maps to persuade landowners that rental rates for some of these poor soils in poor fields were not appropriate. And this value search has continued, but at considerable cost, because you have to figure out with software how to overlay your yield, soil, and local weather data. This is an example of a soybean area that is in need of more seed and more plants if it's going to close canopy before flowering. So I return to my secondary title, which is that precision agriculture in our high-cost, low-return times that we're in means different things probably in different places. In Kentucky, assuming that high cost will continue, and there is some pressure on rent right now and some pressure on inputs, our growers will probably use precision agriculture as efficiently as possible to reduce inputs to low productivity microenvironments or management zones. In Argentina, where inputs are much lower per hectare than we have, I am assuming that if low prices continue, growers might use limited precision agriculture to increase inputs on high productivity microenvironments, which have the best chance of giving a return to the investment in the input and into precision management. With that, I'll bring my talk to a close, and I wish you all a good season. Please keep your tires between the ditches rather than going into them, as this guy did. I say muchas gracias to all of you for my chance to speak with you, and I look forward to your questions. Thank you.
Le agradecemos a John Gru por su presentación y ahora tenemos un espacio para preguntas que va a coordinar y va a moderar Juan Gaona.
Bueno, si quieren mandar las preguntas a los mensajes de texto, ya saben cómo hacerlas llegar.
Lo podemos recordar que es el SMS 0341-586-9877. Reitero, el mensaje de texto 0341-586-9877 a través de Twitter en @Aapresid, Facebook Aapresid Argentina e Instagram por Aapresid. Adelante.
Bueno, mientras esperamos que llegue alguna pregunta, yo, John, te quería hacer una consulta. Hablabas de los mapas de rendimiento y de la simpleza o de lo obvio que muestran los mapas de rendimiento. Pero ¿no ves un valor en esa simpleza y en poder manejar y conocer los potenciales de rendimiento de tu lote para poder manejarlo con cuánto vas a gastar por cada una de esas áreas?
Not getting anything.
¿Tenés traducción para acá? ¿Para John?
Now I can. Thank you.
Le voy a repetir la pregunta si le pueden traducir. Si no ve en los mapas de rendimiento, aunque sea simple la información, un valor en poder predecir la productividad que tiene cada área del lote y poder tener como rinde objetivo esos rendimientos que podemos obtener de mapas de rendimiento anteriores.
Yield maps are done once per year. To use a yield map for total yield potential is very risky. What you really need to think about doing is think about the relative performance so you know one area is higher yielding than another area during, say, a normal season or a wet season or a dry season. We found that the absolute values associated with yield maps are not good predictors of total potential. They're better as relative yield predictors.
Bien, gracias. Preguntan si están implementando en Estados Unidos sistemas de pulverización selectiva como Weedit o Weedseeker para el control de malezas y si están viendo algún resultado, ¿qué resultados están viendo con esa tecnología?
In the United States, very few grain crop producers are using weed identification and control systems. There is a lot of interest, but very little has been done that has been successful and widely adopted. In some specialty crops, in vineyards, in orchards, in some vegetables, this has been more progressive, partly because the value of those crops is significantly greater than our grain crops, and that has been supportive of the adoption of selective, precise weed management technologies.
Bien, gracias, John. Bueno, estamos llegando al final, ya estamos sin tiempo, no tenemos otra pregunta, así que vamos a finalizar la plenaria de John Group. Le vamos a agradecer, realmente muy interesante la visión que nos planteó sobre comparativamente lo que se está haciendo en Kentucky y lo que él ve que estamos haciendo acá en Argentina y las predicciones, su visión para el futuro me pareció interesante. El tema de los costos y de los bajos precios lo estamos sufriendo acá y allá, e impactan las tecnologías que estamos aplicando claramente. De todas maneras, hay oportunidades para ajustar costos, creo, con la agricultura de precisión y con las herramientas de agricultura de precisión que disponemos, pero bueno, son épocas de cuidar las inversiones y cuidar lo que uno va a invertir por hectárea y está perfecto poder revisar todo nuevamente y hacer cuentas. Así que bueno, John, muchísimas gracias.
Nos
Gracias.
despedimos con un aplauso entonces a John Gru.